Bismillahirrahmanirrahim. Dear students, welcome to the Electrical Engineering channel. In this lecture, I will discuss parallel operation of DC generators. Smaller DC generators working in parallel are more efficient as compared to single bigger unit working alone. This gives the following benefits: continuity of service, maintenance, and the second benefit is the increased efficiency. Load fluctuates during the day. Generator works at its maximum efficiency at full load. At light load, bigger unit will draw more power and give less output, but one small unit will be better since it will draw less power. The third benefit of parallel operation of DC generators is the possibility of maintenance and repair, and the fourth benefit is addition to plant. So these are all the benefits of multiple small DC generators working in parallel. Continuity of service means when we have, for example, four DC generators working in parallel and the load at that moment is, for example, very small, so that two or three units can take up the load. So in that case, if one unit needs maintenance or repair, then that unit can be taken out and that can be repaired during the time when the load is small. So when the load increases again, that unit can be added to the other three generators after the maintenance. So this is one benefit. Second is the efficiency. And the efficiency increases when we are using a combination of several small generators. This is due to the reason that if the load is small at the moment, then there is no need to run all the four units at that time. So two or three units can take up the load and fulfill their demand. If we have one bigger unit which is equivalent to four small units working in parallel, then that bigger unit will have to be run even if the load is small. So that bigger unit will take more power and it will generate less power. So the efficiency of that one bigger unit will be small as compared to several units working in parallel, because under small loaded conditions, some units can be taken out and only the remaining units will be feeding the load. Third is the maintenance and repair, and fourth is the addition to plant. If we have such a mechanism that several small DC generators can be connected in parallel, then we will have the benefit of adding more small units to the plant. For example, if we have a running plant which is generating 5 kilowatts of power and suddenly the load has increased to 6 kilowatt, then one small unit of 1 kilowatt can be added to the system. So that is another benefit. Now, paralleling shunt generators, when generator 2 is to be connected in parallel with generator 1, first prime mover is moved and S2 is closed. Then field excitation current is increased until V reads 0, then S1 is closed as well. So here you can see that this is one DC generator and this is generating ampere A1 to the bus bar, right? This is the positive terminal of the bus bar. This is the negative terminal of the bus bar. And this switch is open initially. And this is a rheostat which is connected in series with the field winding. And this rheostat is used to vary the field excitation, right? So by varying the field excitation or the field current, we can vary the flux, and by varying the flux, we can control the output voltage of the DC generator. So after some time, this switch and this switch, both these switches are closed when we have achieved the required DC voltage, which should be available at this bus bar. And now we have to add this generator number 2 to this bus bar. Now in that case, first we will close this switch S2, but this switch will remain open and we will vary the field excitation of this generator So when the second generator produces the same voltage as that of the generator number one, then we can safely connect the second generator to this bus bar. So this will be carried out by initially opening the switch and connecting a voltmeter over here. And that voltmeter will give us the voltage difference between this first generator and the second generator. So when this voltmeter reads zero, it means the voltage of generator 2 has become equal to the voltage of the generator 1. So that controlling of the generated voltage from generator 2 is carried out by varying this field excitation, and we will vary this variable resistance, and by varying this variable resistance we can control the output voltage of this generator. So when this voltmeter reads zero, then that variable resistor will be adjusted to that value, and after that this switch S1 can be safely closed, and after that both these generators will be connected to the bus bar. So this is the standard method of connecting several generators in parallel to the bus bar. Two generators of different ratings share the load according to their ratings. If, for example, if we have first generator and its kilowatt rating is kW1R, so this is kilowatt rating of generator 1. Similarly, kW2R is the kilowatt rating of generator number 2, and kWL is the kilowatt rating of the load, and kW1 is the kilowatt supplied by the generator 1 at that moment, and kW2 is also the current kilowatt supplied by the generator number 2. Then the current kilowatt of first generator will be equal to the kilowatt rating of first generator divided by sum of the kilowatt ratings of both the generators multiplied by the kilowatt rating of the load. Similarly, kilowatt 2 can also be calculated using this expression, and this expression will give us the share of the active powers which are supplied by both the generators to the load. Now, for example, if we have a 10 kilowatt load, right, and kilowatt rating of the first generator is 5 is 20 kilowatt, and kilowatt rating of the second generator is also 20 kilowatt, then in that case the first generator will take up half of the kilowatt of the load, and second generator will also provide half of the kilowatt of the load. So both these generators will share equal amount of the load powers. But if the kilowatt rating of first generator is high and kilowatt rating of the second generator is low, then the share or the contribution of the kilowatt supplied by the first generator will be higher than the share of the kilowatt of the second generator, right? So that can be calculated by using these two expressions. So these two expressions will calculate the individual kilowatts which are supplied by the generators to the load. In another case, we can have unequal no load voltages. So for example, if both the generators have different voltages at no loaded conditions, then that no load voltage of the first generator will be E1 and that of the second generator will be E2, right? And R1, R2 are the armature resistances, and V is the common terminal voltage because common load is connected to both the generators. So in that case, V will be equal to E1 minus I1 R1, and V will be equal to E2 minus I2 R2. So I1 can be calculated by rearranging this equation, and I2 can also be evaluated by rearranging the voltage equation of the second generator. Now we can take the ratio of these two currents. So I2 over I1 will be equal to E2 minus V divided by E1 minus V multiplied by R1 divided by R2. Now we know the value of E2 and E1, and E2 is equal to K2 and 252, and E1 is K1 and 151 minus V multiplied by R1 over R2. So this is the expression of the induced EMF of a DC generator. And in this expression, apart from revolutions, number of RPMs, and the magnetic flux, all other terms are constant. They are represented by K2 and K1 for the generators. G2 and G1 respectively. So that is all about our today's lecture, and in this lecture we discussed the parallel operation of DC generators. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.